So our next guest comes from Munich. He's a founder and managing director of PlanV, with a massive track record in system-on-chip integration. He's been doing everything from CVA6 subsystems and cache coherence to formal verifications. So please welcome Massimiliano Giacometti.
Thank you very much for the nice introduction. Yes, and good afternoon, everyone. So my name is Massimiliano, and I would like to talk to you about what we do, and especially about how we try to help bridging the gap between research and the industry. So first, I get always the question about our name. Is it a letter? Is it a number? The introduction was correct, so officially the name is PlanV. And the reason of the name is that it took us a few iterations until we were able to find a viable business model for the company. So it's PlanV, but I wouldn't be here today if we also hadn't something to do with RISC-V. What we do and why we do this. So we are a service company. Basically, we help other companies in designing and in verifying chips. Here there is a list of good news why in 2022 it was a good idea to start this kind of business. I have to say this is essentially a lie. And the reason why it is a lie, well, the real reason why I started this company is that back then I was on the verge to lose my job. And this story is also related to RISC-V. Basically, the company I used to work for that company, we've been developing a RISC-V CPU for security applications. We taped out the chip. Technically, it was working as expected. Unfortunately, it turned out that selling security devices was difficult. And so management decided to close the project, and I had the opportunity to start working as a web developer for the same company. It was not that appealing to me. Nothing against full stack development, but it was not my job. And so I decided to go back to my previous activity as a freelancer, freelance design, but I started talking with former colleagues. And we had the idea to do the same as we did before, so offering design services, but doing it together might have been more fun. And it turns out it actually is. Today we are a team of 7 engineers, relatively young, so we're all below 45 years old. My colleagues come from all over the world, so from Spain to Australia. This is very interesting. It gives us the opportunity to have direct exposure to markets which we probably wouldn't be aware of if we were just based in Munich. And also, it is a solution to reduce costs. So without offices, it was very beneficial, especially at the beginning. We have a strong bias towards R&D activities. We try to outsource as much as possible for what is administration stuff. And, well, we still do some business development and sales because we need some cash flow to pay our collaborators. But we try to do fun projects and interesting stuff, mostly related to RISC-V. And this is what I want to show you now. So, why RISC-V? A very interesting feature of having an open source architecture, as it has been said multiple times already, is that it allows projects, collaborative projects, so collaborative engineering. A great example for this, I think it is what comes out of the Open Hardware Foundation. I'm not sure whether you know what the Open Hardware Foundation is. Davide Schiavoni, I think he was expected to present the group today. Unfortunately, he's not here, so I will take a couple of minutes to advertise this initiative. I personally like it a lot, so I'm happy to do this. The Open Hardware Foundation is essentially a working group within the Eclipse Foundation. And it is a platform which promotes and which helps and coordinates research institute, universities and companies to work together to develop open source CPUs. The idea and one of the main goal of this group is to promote and to develop industrial grade CPUs. And this means that the quality of the IPs must be usable directly for actual products. So one of the core parts of the development is also verification activities. There is a lot of focus on these aspects, and they also promote and offer verification infrastructure for the CPUs. Here, the project I would like to talk about is CVA6. Maybe it was already mentioned before. Anyway, it is a 6-stage CPU. It is Linux capable, and at the beginning it was a single issue CPU. Now there are a lot of options which you can choose. One of these is also the possibility to have a superscalar architecture. Then you can have a 64 version, 32 version without cache, with cache. It is a verification nightmare in the end. But it is very flexible and a very interesting tool to work with. We are working with Thales on this CPU, and there are a lot of other groups which are also contributing, but we are working a lot with this company to help the development of this project. Thales, maybe you know, it is a French company. They do a lot of work in aerospace, defense, security, and automotive. They are at the moment the maintainers of the CVA6 project, and they are obviously interested in the development of this IP because they want to integrate it in their own products. They are interested in both hardcore macros and softcore versions, so they want to do it. They want to integrate it into custom silicon devices or in FPGAs. And what we've done with them is helping, like, refactoring the code to help code maintainability. We have been doing some FPGA porting to Altera FPGAs. We've been doing FPGA optimizations because they were interested in having the smallest possible CVA6 CPU for their FPGA-based products. And most of the contributions we've done are publicly available. Some of the contributions remain closed source and proprietary at Thales. So this is, I think, a very good example of how RISC-V and open source nature of RISC-V helps bringing technologies from research to actual products. Another example of the use of CVA6 is for this RISC-V subsystem, which we've developed for another client. The project there was a high-performance computer, and they were requiring a simple, relatively simple subsystem to be able to monitor and configure the big HPC machine. And they wanted the system to be developed quickly and cheaply. And the solution for this was using open source IPs. So again, CVA6 was the heart of the system, and then we took everything possible from the library developed over the years by the Pulp team. So we took the L2 cache, DMA, interrupt controllers, debug modules, a bunch of standard peripherals, and it was relatively easy to glue things together and to have rapidly a working system. Next in the list is an emulation platform for fault injection. So in this case, our client wanted a system to be able to emulate fault injection before silicon, especially on FPGA. The system then had to basically and we wanted to do this via software. So the idea was to take an existing microcontroller. In this case, we took the Core 5 MCU, again, from the open hardware family of products. And we modified it so that it was possible to emulate fault injection from an host controller and monitor the execution of the software. What we did was basically changing the debug interface. What we removed the existing JTAG interface. We used the QSPI port because it allowed faster data transfer. We modified the debug module, adding control and status register, which were able to control the execution of the software and trigger jumps in the software when certain instructions were encountered. And finally, we also developed an hardware tracer to be able to monitor the execution of the system, dump everything, send it to the host controller, and then do offline analysis. And in this case, I think that the benefits of open source are, well, the possibility for teams, different teams from different companies to work together on the same project without the hassle of NDAs. Again, this is a topic which has been mentioned before, and NDAs can be a real pain in the neck. To give you an example, for another project, we have one supplier which must sign an NDA with one of our subcontractors, and it's been taking now, well, this activity is has been halted for 10 months, more or less, because the legal departments of these two entities cannot agree on the content of this NDA. And what is ridiculous about this is that in the end, the project will be open source. So I don't know what is the fuss about it. Anyway, we have to live with this. So other interesting aspects of this specific project is that we already had a lot of software available to be able to run experiments and to control the system. So we had free RTOS, we had OpenOCD, again, another open source project, which we have been able to modify so that it was possible to adapt it to our modified debug interface. And well, next step for this is, of course, the client has been able to demonstrate this infrastructure on an open source project, but this is not their own project. So the next step is for them to port this example into their proprietary CPU, and then they will hopefully use it for actual testing of their systems before production. The last example is a project is a project sponsored by the German Cyberagentur. This is, in a nutshell, the German DARPA. A bit smaller in size, but the goal is the same. So they are sponsoring research activities targeting cybersecurity and defense applications. Sorry. We're working on this project together with the University of New South Wales and University of Gothenburg. And the goal of this activity is basically to develop a reference design for trustworthy embedded systems. And this is based on several layers. So the bottom line is a RISC-V-based system on chip, on top of which we have the secure microkernel SCL4, on top of which there is the actual operating system, which is Lions OS, and on the application layer we will have non-secure application, human-machine interfaces, and other control systems, and all of these processes are guaranteed to be confined, so that there is no, so that the security properties of the systems are basically guaranteed, and meaning that there is no exchange of information between security domains which should not see, should not have exchange of data. Data are confined, the functionality is guaranteed. So let's have a bit deeper look at what is happening in all these layers. So the CPU, again, is CVA6. I will not talk much about this since I've already done. The only thing I want to underline is that we are focusing for this specific project on the verification of the MMU, because it is a critical component used by the microkernel to guarantee the security properties. So it is very important that this block works as expected. Then SCL4, as I said, it is an open source microkernel. It provides the basic functionalities which are required by every operating system. It is security oriented. It provides confinement, confidentiality, and integrity properties. And the very interesting thing about this microkernel is that it is formally verified. So it means that you have basically the guarantee that everything which is declared the microkernel can do is actually done properly, and you have the guarantee of these functionalities. If you're interested, one interesting real-world example of an application for SCL4 is the DARPA HACMS program. Basically, what they have done is they implemented the control system of an helicopter using SCL4 or without SCL4. Bottom line is the version without SCL4 was hackable. The version with SCL4 was not hackable. So good results for them. And here what I want to show is how an open ISA can also bring new features into the game. So what is offered by CVA6 is also this custom instruction, which is called FENS-T. And this FENS-T instruction is basically an instruction which does resets the microarchitectural state of the system, and this is used to prevent spilling of information between security domains when you have a context switch, meaning that one process which has access to the secret cannot encode the secret in the state of the machine, and then when there is when the control goes to a different process, which, for example, has access to a communication interface, this cannot read out the state of the machine and then send the message to the outside world. And the possibility to have these kind of features is given by the fact that we have an open source CPU and an extensible CPU. I think this is the only system which implements this kind of feature, so it is extremely interesting for trustworthy systems. Lions OS, I'm not an expert in this. It is basically the operating system layer. What I know is that it makes it possible, it makes the SCL4 basically usable, because if you take it as it is very hard to manage, and this makes it more palatable for software developers. Verification story is still ongoing, and it is part of our project. And The last part is how the operating system layer and the hardware layer are being developed together in a way. So one of the goals of this activity is to provide a framework which allows the co-verification, formal co-verification of device peripherals and the corresponding device drivers. And to do this, my colleagues are working on this kind of framework. It is based on all four property specification languages for the hardware part and Pancake for the driver part. The story here is still ongoing. We've just started experimenting with the first driver, but I'm very curious to see the results in the future. So this is the last slide. I thank you very much for your attention. A couple of links here, and I give back the mic to Tan.